Tá aqui, por isso que eu pus aqui, ó. Tá ligado aqui, né? Well, good morning, everybody. And we are just about to start the intensive course of epidemiology for the evaluation of intervention effectiveness. And we have the pleasure of having with us as a visiting professor, Dr. Eduardo Simões, who is director of the Center for Medical Epidemiology and Population Health of the Department of Biomedical Informatics, Biostatistics, and Medical Epidemiology of the University of Missouri. He has been previously with us in several other times, and now he's going to stay for 2 weeks, and he is going to present this course for you. And on not this Wednesday, but next Wednesday, he will give a webinar on metabolic syndrome. Without further delay, I'll give Dr. Eduardo the floor for him to present his course and give the first class today.
Good morning, everybody. Thank you, Dr. Ramos. Dr. Ramos and I go back many years of friendship and partnership. And like he said, this is probably one of my 4th or 5th intensive training over the past many years. This course is a little different than the ones I have given before. The focus is really on the evaluation of population-based intervention effectiveness type of study. And we're going to cover not only the ideal setting, but also the not so ideal settings and how we still develop an evaluation. And we're going to end up this course with last day with a few examples of not so ideal settings in which you still can do an evaluation. I hope you can bear with me that the course takes about 6 full days. And now I'm going to give you some reading. I'm going to send an email or message to all of you so that you can anticipate every day the reading that you may have on the 2nd day, 3rd, 4th, 5th, and 6th day of this course. First day, evidently, you don't have any reading, but you could read retrospectively, something I'm going to give it to you also for the day of today. So let's talk a little bit about the organization of this course. Like I said, the course structure is 6 days. The focus is population-based interventions. How do you evaluate them? And what's the epidemiology of it? That's what we're going to do. So in the first day, which is today, is going to give you some basic foundations. Many of you already know, it'll be like a refresher. You're not going to have to study too much. And then out of that, we're going to talk a little bit about the basic epidemiological design, which is going to be in the tomorrow, actually, on Wednesday. We cover the basic epi design, cohort, case control, cross-section. Very important because they are the foundation. And when you need to resort to a natural experiment, sometimes you need to go for one of those observational studies. Then on Thursday, which is 2 days from today, we're going to get into the nitty-gritty of the really randomized trials. 2 types of randomized trials. The individual level data collection and analysis. That means the individual is the unit of selection, or random selection, as well as the unit of random allocation for the treatments. That's all called randomized clinical trials. We're also going to discuss the cluster randomized designs. Very important, because in that one, the unit of sampling is a cluster, is a thing, is not the individual, but the unit of analysis still at the individual level. So you're going to learn a few tricks how to analyze that. And why is that important? Because many of the other design we're going to show you on the second week, which is next Tuesday, requires you to understand this foundation of clustering. So you understand how we can, oh, is that what a step wedge is all about? And that's how we do it. And some of the other variations, we're going to learn about natural experiment, what they actually mean. And then we're going to learn about some other types. Actually, when we did this orientation, we missed out maybe one or two other designs. We're going to look into difference and difference. So it's there, but it's not. We're going to look into regression discontinuity and interrupted time series in addition to the step wedge or natural experiment. So these are very important evaluation designs. They're very seldom used in South America or Latin America for that matter. And then we're going to end up discussing implementation science. When you go from, I learned that's effective, something that was efficacious, now I'm showing that's effective, how do I implement that? What are the bases for implementation? And how do I disseminate that? That's the implementation dissemination of science. I'll have a whole lecture ready for you. And then we discuss how we pull it all together through systematic reviews and meta-analysis. And we're going to look into a little bit of the methods. What are the requirements for you? You need to have some basic foundation in statistics and epidemiology. We're going to refresh you in some of those foundations today. Okay? We're going to look into some statistical foundation, and there's another lecture on measurement errors that I'm going to look at over with you. Okay? But first, let's get started on the first lecture, which is measure of disease occurrence. We're going to stop, go back a little bit to the statistical review, and finalize with the other metrics of that lecture. Very important, the genesis of this course is actually back nearly 20 years ago. In 2003, I created a project for the Centers for Disease Control and Prevention in South America, especially in Brazil, but also included Colombia, that we offer universities in Brazil and in Colombia, as well as other partners, the opportunity to evaluate their physical activity programs. We are very focused on physical activity, but that dimension could be expanded to anything. And at that point, we have learned through a maximized literature review, there was very little foundational work on what works, what doesn't work, meaning very few evaluation trials. At that point, when we initiated this project, there was almost nothing about physical activity. After we finished the project, we had evaluated 2 large physical activity programs in Brazil with natural experiments and a little bit of a quasi-experimental design at a later date. And I got to be invited to be part of one of the journals in epidemiology in Brazil, RES, from the Minister of Health of Brazil. And at that point, I was hoping to see, after 15 years, more and more evaluation designs. To my dismay, I haven't seen that many. That means I'm bringing something that I think you need it. And if you learn how to do it, I want you to use it. And I'll be your partner if you want to. You can contact me. I can help you to implement those studies. Without further ado, let's go back to the lecture. I think I need to, well, I can find it. It's here.
Not necessarily do this.
Oh, I don't need to go there?
No.
Oh, here. It's there. Here.
Yeah.
I can do that. Sounds good. No, don't worry.
Yeah.
I know. So let's get started. Already took 50 minutes of this course. We're going to do just a very brief review of a very basic measures. So frequency measures, measure of central location, frequency measure characterize only part of the distribution, and frequency measure compare one part of the distribution to another. So you all should know that. It's more like a general review of this topic. And these lectures are going to be available to you after this class today. All your lectures, except for the last day, will be available to you. The last day, one of the lectures, you need to have a revision done so that I can make it available to you. But you'll be able to see it and to read this material, which is very rich in information. So by frequency measure, we're talking about common frequency measure, like ratios or proportions and rates. Let's distinguish them, okay? Most of them are presented as numerator divided by denominator multiplied by 10 to the nth power. So that's a typical way. For instance, 10 to the 0 is 1, 10 to the 1 is 10, and 10 to the second power is 10 multiplied by 10, which is 100, as you should know. So the fractions can be multiplied by 1, 10, 100, 2,000, and so on. So this multiply vary by measure. You're going to see a lot of that in traditional epidemiological measure. You're going to see in about maybe half an hour. So first, the most important measure is your count. How many events happen? It's a count. 55 breast cancer cases. That's a count. A ratio is a little different. is it provides the relative magnitude of two quantities or a comparison to value. You divide one interval ratio scale variable by another. So it's called ratio. Okay, you divide one variable by another. So if you have height, you divide by weight. If you have, whatever is the rate or count you have it, you divide by another count of another thing. That's a ratio. The numerator and denominator need not to be related. Evidently, if they are related, it's still a ratio, but it's not the ratio I'm talking about. The ratio I really want is those they're not related. So therefore, one could compare apples, with orange, or apples with number of physician visits. Doesn't matter. I count 10 apples, I'm taking the ratio of 10 apples divided by 10 physicians, 10 apples by physician. That's a ratio. So number of rate of events, items in one group divide by the rate of events or counts in another group. So this is a typical example. I have 55 women with breast cancer out of the total number of women without breast cancer. That's a special form of ratio. You're going to see that later on. That's a proportion. So property and uses of ratio, male to female ratios. That's the typical stuff we need to use, ratio of control to cases. So I'm going to skip that because you should know that, but it's a good reminder. Read it over if you think that you're still confused, because we're going to use the word, the terminology all the time, like in risk ratio, which is actually the relative risk, the risk of one group relative to the risk in another group. We're going to use the word rate ratio, which is the incidence rate in one group divided by the incidence rate in another group. We're going to use the word odds ratio. It could be a lot of things, but it's a ratio of an odds of a group exposed to something divided by a group exposed for something else. It could be something different. It could be the odds of disease divided by, in one group, divided by the odds of disease in another group. It could be the prevalence. So as you remember, we're going to talk about that. There's prevalence odds ratio, there is exposure odds ratio, and there is disease odds ratio. Yeah, 3 odds ratios. So calculating a ratio, I'm going to skip that. You read it over. Examples, you have it. Commonly used epidemiology ratio measure, I wanted to mention, to use death to case ratio. You can read about it too. These are examples of ratio. For instance, advance of coronavirus epidemic in selected countries in 2020. And you can see the number of infected after 50 days, the number of deaths. And you can create ratio, death to case ratio. It's the number of deaths divided by the number of cases after 50 days. It's a measure called case fatality. Okay? And you can have other similar measure of ratio. I'll skip that. Let's go to proportion, which is a special kind of a ratio in which the numerator is part of the denominator. It's just a subset of it. And you take that subset out of the total and you multiply by 100, you get a proportion represented by percentage. Okay? You should all know that too. This is a reminder. You can read about it. Never get confused with the word proportion, rate, and ratio. We're going to talk about rate very specifically later on. You're going to learn that it's only one rate in epidemiology, the incidence rate or the incidence density. Probability, that's a special case of a ratio. If a student is randomly selected from the school with 600 females and 400 males, the probability of being either gender is, you should know that, right? So there's 400 males out of the total of males and females, that's 40% chance of being a male, right? And women is 600 divided by the total of male and female together, that's 0.6, that's 60%. So the ratio male to female is approximately 400 to 600. So I extract a lot of measures here. I extract what's the, in a random sample of these 1,000 people, what's the probability of selecting a male? 40%. What's the probability of selecting a female? 60%. And what's the ratio of male to female? Is 0.666, which is 0.67%. That's 67%. Okay? So that means there's more women proportion than men. Definition of rate. Rate is a little different. Measure the frequency which an event occurs in a defined population over a specified period of time. We're going to repeat that again later on in the right context. We're going to talk about incidence rate. But I'm just give you an early preview of it. Rate calculations require observed number of new cases over a time period, and you need to measure what the size of the population is in terms of density. And the density is how many minutes or days or hours or months or weeks of time observation is provided by that person. Is this, if you had a study and you need to follow people up, okay? So that's what you wanted. But you can measure that indirectly when it's a large population, talk about like a city. It could be the size of the population that year, estimated at the midpoint in the year, they say June or July, multiplied by 1, because you're dealing with a 1-year rate, right? So if a population of São Paulo has 14 million people, that's your density, that's your population density is 14 million person years, because you're talking about 1 year, 14 million person year. And whatever is the incidence that you get for, let's say, a rare cancer, thyroid cancer, okay? It's going to be a 1 in 10,000. So we have about 14 million people. We're going to have 100 cases here, okay? Now, 1,000 cases. You're going to have 1,000 divided by 14 million person a year. So that's your thyroid cancer incidence rate. You're going to see that more in more detail later on. But you can estimate for large population the density, the person time year, by multiplying the size of the population by 1 year if it's large population. When the numbers are too small, I'm going to show it to you statistically. You can't do that. If you're following up 500 people, 1,000 people over 1 year, and you're estimating person month or person weeks, and you try to say, okay, well, the population is 1,000, I say it's 1,000 person a year. You're going to make a mistake. I'm going to show you why, because the risk and the rate are different things, and you're actually estimating the risk instead of the rate when the numbers are small. We're going to talk about that later. So usually the formula rate is number of cases, population at risk multiplied by 100. But remember, this only works, this formula for large population epidemiology. For small population, you need to calculate how many person years of observation each person gave to the follow-up period of observation. I'm going quick on this because this is review for all of you. Then you have an example rate, another example rate, more example rate from I've seen it, I've shown it to you before. Before shows a count death per cases. Remember the ratio of death per number of cases? Now I'm showing you the incidence rate per 100,000. So again, this is a little table that shows the difference between them: morbidity, mortality, survival, natality, birth. And you have this crazy table here: risk ratio, relative risk, rate ratio, proportions, attack rate, incidence, secondary attack rate, point prevalence, pre-prevalence. Remember, in proportions, there's two things called rate: attack rate and secondary attack rate. And many people call prevalence rate. But they are actually proportion, not a rate. For a rate, you need a measure of time in the denominator, person time of observation. You can extrapolate if you have large population in a city, and it says whatever the city size per year. So you multiply by 1 year, right? So that's a person year estimation. It's a rate. But usually when you're not in that scenario, you should not call rate. So the word attack rate is a misnomer. It's a wrong name, but very much called. It's actually the risk ratio. And then the secondary attack rate is another misnomer, should be just secondary risk ratio. And point prevalence and period prevalence is better than prevalence rate, which is many books of epidemiology. And actually in Portuguese too, taxa de prevalência. That's wrong, but that's okay. Proportionate mortality. It's a true proportion. Where are the rates on the side here? On the left hand side, person time incidence rate. That's the only true rate in epidemiology. The crude mortality, case fatality, kind of can be called a rate as well as cause specific mortality. Everything is mortality should be called a rate. If you have large population, person year, or if you follow people up over time and see how many die. Because every death is a new event, right? You're going to see later on the incidence rate is always the new case that occur over a period of observation divided by the total population at the beginning of the follow-up and the number of person time that the person provided to the follow-up. Is the summation across all the people being followed up. So now we're in the territory that you review ratio, proportions, rates overall. Let's be in the territory of defining what is a risk, or the so-called cumulative incidence. So risk, we're going to define, we're going to show the numerator, denominator, many times called attack rate, which is a wrong terminology. Should always be called risk, is what it is. Okay? It's a probability. Risk is a probability. There's a proportion, but there's also a probability. Many times people call prevalence rate. They are also proportions. Like I said, cumulative incidence rate, it's just risk. It's not a rate. Attack rate is not a rate. It's just risk. The incidence rate is the true rate. Remember that. So incidence refers to the occurrence of new cases of a disease over a period of time. Every time you're observing a population or group of people over a period of time in a study, a cohort study usually, or through surveillance systems, you're observing a whole population over time, the new cases occurring over that time period out of that population, arising from that population, they are incident cases. Remember that, new case. So the numerator of a cumulative risk or risk and the numerator of the incidence rate, which is the true rate, it's the same. It's a new case of the disease occurring over a time period specified to initiate at date X and finish at date X. Okay, that's your incident case. So it's expressed as new case of disease or injury during a specified time, divided by the total population at the start of the period. Okay, total population at the start of the period. So here's a little example here. You can see that the population, these are all the number of people who are being followed up over this period from October 1 to here. This sign here means date of onset of the illness. The arrow down, date of death is a plus, date of recovery is a way up. So when you start on October 1st, there's 1, 2, 3, 4, 5 people being followed up. Okay, 1, 2, 3, 4, 5 people. So you can estimate how many die out of these 5 people over the time period, and you can count them. And if you open that observation period, you can also include those the 3 others initiated later on, and even later. And there's 4 others. 1, 2, 3, 4. They initiated later on. So you have 1, 2, 3, 4, 5, 6 at the beginning of October 1st, 2004, and 4 others who came throughout the period of observation. Okay? So you can say, if I'm interested in the incidence of new cases, and new cases defined the date of onset of illness, arrow down. So I had, over the time period of these people, already had the incident cases. I cannot measure how many of the incidents already are, but I can count the incidence of death among them, among these 4. And over a time period of, let's say, from October 1st, 2004 to September 30th, 2005, exactly a year. Okay, out of these 4 people, only 1, 2, 3, 4 died. The others are survival, number 1 and number 10. Okay? And you can calculate many other types of rates in this little example here. But think about those guys here, 1, 2, 3, 4, 5, 6. That you initiate the follow-up on October 1st. What happened? A blackout? So out of those 4, 1 developed the condition more or less at the beginning of the follow-up period between October 1st and April 1st, 2005. The second one, number 4, developed after April 1st, but still before September 30th, before a year. The next one developed at around close to September 30th. The next one, which is number 8, developed a condition that died, in this case, we're interested in death, around March of 2005. And the last one is a survivor. It did not develop the condition. So out of 6 people, you have 5 new incident cases. Divide by 6, so 5 over 6 is your risk. The risk of dying among the incident cases of such and such condition is 5 over 6. That's your risk. We're going to show more examples of that. So it is the probability of developing disease for those who are at risk for developing disease. As you, because I'm interested in death, that the plus sign, anybody, even the person who already had the disease, can die. So the condition, the disease of my interest in this case is death. So all of them had some kind of a disease already, the incident case of the disease. But I'm interested in how many of those incident cases will die. That's a special case of a rate. That's a case fatality rate. out of X 6 cases, I have 5 deaths. Okay? So it's 5 over 6. That's your death rate for those cases. That's a case fatality rate. So it's a measure of occurrence, a new case, therefore it's an incidence measure. Risk is an incidence measure. You measure the probability of something occurring over observation period of time among people who are at risk for that something to occur. They are at risk. They need to be at risk. Okay? So in that crazy example I created here for you. Oh, it's not going back. It's stuck. It's frozen. Yeah. It's frozen here and there. Oh, you have a magic hand.
No, it stopped here, but it goes forward, but not backward.
Okay, so I have to be careful then. Won't be able to go back to the example, but you can read it later on. So it's a proportion. So a risk is a proportion, is a probability, is the measure of incidence, measure of new cases occurring in a population of people or whatever. If you can calculate the risk for animals, if you're a veterinarian, you can calculate the risk for plants, if you're a botanist, okay? It can be anything, as long as that thing that you're observing over a period of time has a count, you know how many people you're observing at the time period that you initiate the observation period, and you're counting how many of those develop a condition which they are at risk for developing that condition. So they need to be at risk. That's a very important concept. They cannot have already the condition you're trying to wait to see if it happened, right? So they are at risk for that to develop. So in a study of diabetes, 189 diabetic men during the 13-year follow-up period, calculate the risk of death for these men. In the study of diabetes, 100 of the 188 diabetic men died. So 100 die out of 189 diabetic men over a 13-year follow-up period. So I basically had 189 diabetic men, follow them up for 13 years. Okay? So calculate the risk of death for these men. There are 100 deaths. That's your event that you're interested in occurring over the time period of observation, 13 years. The denominator at the beginning of the follow-up, 189 diabetic men, all at risk for dying. Okay? They're all at risk at dying. So you have your 10 to the second power, that's your 100, okay? Your risk is going to be 100 divided by 189 multiplied by 100. You produce your risk by percent. If you want to, or you could present as 0.529, but you present as a percent, a very acceptable way to present it. So the risk of dying among diabetic men over a 13 years period was about 53%, okay? So it's more than half of the men died within a 13 years follow-up. That's your average risk of dying if you're a diabetic. Another risk, in an outbreak of gastroenteritis among attendees of a corporate picnic, 99 persons ate potato salad, 30 of whom developed gastroenteritis. Calculate the risk of illness among persons who ate the potato salad. Well, that's my incident case. 30 persons developed gastroenteritis. They all ate the potato salad. And my denominator is all the people who ate potato salads. So it's 99 people. So I divide 30 by 99, multiply by 100, and I'll obtain my risk or attack rate. That's what epidemiologists call wrongly. It's not a rate. It's just a proportion. A rate, you have to have denominator, including the function of time. Okay? This is just a proportion. It's a probability. So you could say that the probability of getting gastroenteritis, developed gastroenteritis, among those who ate potato salad was 30.3%. Cumulative incidence, which is what we calculate in the risk, is always the number of new cases divided by total population at risk during the observation period. And you can extrapolate for large population. In the previous two examples, we're talking about small sample of people who being followed up over time. One prospectively, the diabetic example, the other one retrospectively, because you had a list of people who attended the picnic banquet, and then you basically identify how many ate potato salad, and how many of those who ate potato salad developed gastroenteritis. So the retrospective kind of cohort investigation, where the other one is a cohort. You're going to see that later on. Whereas here I'm talking about surveillance data for the general population. So total population of, 50,000 women and 55 incidence breast cancer. It's the same as saying 110 per 100,000 women. Okay, new cases, 100 new cases for every 100,000 women. That's your risk. So the denominator should be limited to the population at risk. Persons who have the potential to get the disease has to be included in the numerator. So if I'm calculating the risk, for an infectious disease that comes from immunity, many, like measles, okay? If the person had been vaccinated or had already developed measles, can they be in the denominator to be followed up to see if they will develop measles in the future? No, they can't, because they are immunized, right? They have an immune response to measles. They will never develop, because measles you develop only once. You have lifetime immunity against measles, okay? So in that way, they need to be removed from the denominator if you're doing a follow-up to see how many will develop measles over time, or any infectious disease that comes from immunity. Likewise, should we include you doing an instance of prostate cancer? Can you include women in the denominator? No, they're not at risk of developing prostate cancer. They don't have a prostate. It doesn't matter in epidemiology. Even if they are transgender, they cannot be the denominator because they don't have what? A prostate. Likewise, if it's a man that became a woman later on, they need to be removed from the denominator because they don't have a uterus for uterine cancer, or for cervical cancer, or for ovarian cancer, or for fallopian tube cancer. So there's a lot of things that you need to be aware of this at risk. Immunization, infectious disease, depends where your area of interest is, or things like that. For cancer is the gender defining the denominator. They gotta be at risk in the denominator. And the new cases in the numerator, always. Assumption, there's assumptions here. There's the period in which persons are followed up, study period. Okay, all persons in the population being followed are at risk, and all persons in the study are followed up at the same amount of time. So you either do that by estimating average amount of time to be similar, like you're doing a total population being evaluated for a whole year of a county or city. But if you are doing a study, you actually have to tally. You have to monitor people. And that's why long-term follow-up, that you only measure people every 2 years, every 3 years. You're losing a lot of information. You don't know what's going on in between. You need to do more constant measurement to see if they're being followed up. What if you lose people to follow up? So lost to follow up. I develop a study. I engage and involve 100 people in my study, and I'm following them up for 2 years. A year later, I go measure again. I lost 50 of them. I don't know when they left. If they left month 1 or month 2 or month 12. So I'm going to give them 12 months follow-up period? No, I'm going to give them the average follow-up period, half a year. Okay, I'm going to more or less estimate, make a mistake, but by laws of large numbers, if it's over 50 to 100, we may end up getting this number right of how many person months of observation I gave to the denominator of this person being followed up, which is going to be important for incidence rate. Usually when you're calculating risk, you're also interested in person time for the incidence rate. We're going to see that next. I put this here just as a reference. There's a word, attack rate is always risk, folks. There's no such a thing as attack rate, even though you're going to see that in many, many books. It's an old term used in the turn of last century, and then people still attach to it. Secondary attack rate, it's also not a rate, it's just secondary risk, meaning I had an infectious disease person. That was a case number 1. That's a primary case. And then I have contacts of that case develop the infection. They are going to be my secondary incident cases. So that calculation of the original denominator is called secondary attack rate, okay, which is not really a rate. I give 2 examples. You can read about it. Okay, risk usually presented in epidemiology, like I'm showing this table to you here. Okay, you have A cases, B cases, C and D. And C and D could be just N1 exposed people to something. Remember, the risk always imply a follow-up period, and I'm observing people in a study. We're going to see that in the next lecture tomorrow, okay? When you do a cohort studies and case control, you're going to see how those measurement comes about, and they relate to each other, okay? How we create a measure of occurrence, and from that, I estimate a measure of association between two factors or one factor and an outcome. So usually I present it like that in a 2x2 tables. I'm giving you an anticipation of tomorrow, and you can see they are all in numerical, and you have something called the risk in the exposed group, R1, which is A divided by N1, which is N1 is the summation of A plus N1 minus A, okay? So you can figure out that easily through simple arithmetics. If you have, let's say, 10 people here are my total cases exposed, and I have 5 cases, then 1 minus A is going to be 10 minus 5 is going to be 5. Okay, so you can fill up the table very easily. Likewise, you can do that laterally. M1, M2 should be M2. So it's a typo here. It should be M1 and M2, N1, M0, or M1, M0. That's another way to present. It's just a presentation. Don't get confused. So there's something, every time you do a measurement in epidemiology, the risk, you need to estimate how much error you can have in that measurement. And that's the cumulative incidence. The risk is your new cases, I divided by N, and these are the confidence interval. You have a standard error, okay, that you estimate from that measure, and you multiply that standard error by 1.96, okay, the standard error around the risk, and multiplied by the 1.96, which is the Z standardized value for the distribution of all possible risk estimates in a theoretical distribution. That's going to give you the confidence interval. And if you do plus the risk plus or minus the confidence interval, you end up with your confidence. You are as confident as this confidence interval is going to give you. So when you say the risk is 0.5, and it could have been 0.4 to 0.6, that's your confidence bound, that you're confident that if I see a risk of that size, on average, I'm very likely to be true 95% of the time between 0.4 and 0.6. Okay? So that's your risk estimate. And I give you some numbers. You see the formula, how it's calculated, using this N1 minus A. You can go back to the formula and say 1 minus R divided by N, multiplied by square root of R, or you can do with the adjusting correction here, 1 minus F, and I give you the formula here. You can see how it's calculated. Okay, you have more confidence interval, you have an exercise. So let's do another one. We'll use the same formula. You have 100 deaths, you have 189 diabetic men, and over a period of time, 13 years, 100 of them developed the condition, which is death you are interested in. So you have 100 divided by 189, that's 0.529. So what's the confidence interval around that? You know how to do that now. It's going to be that proportion, 0.529, then multiply 1 minus that proportion, divide by the total N, square root of the whole quantity. Okay? Why? Because this is just coming from binomial distribution. That's going to be the next hour. We're going to talk a little bit of review of those statistical foundations, because later on you're going to need it when you're talking about randomized trials, or when you're talking about cluster randomized trials and the other type of regression stuff that we're going to do. You're going to learn that this is very simple, but fundamentally important to understand why I'm having a standard error calculated with P, that's proportion, multiplied by 1 minus the proportion. Let's go. P that multiply Q divided by N square root of the whole quantity. Because it's coming from a binomial distribution. Okay? So each one of those columns, exposed and exposed, consider them each individually a territory of binomial proportion. I have 54 out of 366 people. That's a proportion. And I'm looking for a binary variable. That's going to be yes, I have it. No, I don't have it, a condition. Okay? Among those who are exposed and unexposed, yes or no type of thing. So you have a binomial scenario. You're going to see that in the next hour. We're going to do a little review of the statistical distribution underlying every calculation we have in epidemiology, including those complicated ones in randomized trials, cluster randomized trials, stepwise trials, and so on and so forth, and the natural observations coming out of natural experiments. So here again, this is just proportion. You see the formula is about the same, and you calculate your confidence interval. You can replicate that easily. Okay, folks? Okay, what time is it now? Is that 1 hour already?
10 to 10.
Is that 1 hour?
No. Yeah, 10 to 10. 50 minutes.
Okay, it's 50 minutes. So let's do a little bit on prevalence. The difference between a risk and a prevalence, as far as statistics, is nearly none. As far as statistical distribution, both are proportions, both are derived from binomial distribution. Okay, so I'm going to give that, and then very quickly you're going to read the remainder of that, because I'm going to skip that lecture later on and move to the statistical foundation for you for the next hour. But let's do for the next 10 minutes, finish the prevalence. Also proportion. Prevalence sometimes refers rate. Prevalence rate is the proportion of person in a population who have a particular disease or attribute at a specified point in time. I could say the proportion of chairs in this classroom. That's a prevalence of chairs. There are defectives, the proportion of defective chairs. So out of, let's say, 2, 4, 6, 7, multiplied by about 8, 60 chairs here. Let's say I have 10 who are defectives. 10 divided by 60, that's the prevalence of defective chairs out of the total number of chairs. So it's just a proportion like the risk, and both follow the same distribution statistically. We're going to talk about that later. So prevalence is sometimes refers to rate. That's a wrong terminology. It's not a prevalence, it's just a prevalence proportion. Okay? It differs from incidence because the incidence, if I have observed period of time, see, year of 2004, every new case of cancer coming out of starting January 1st or to December 31st of 2024 is an incident case of cancer. Every new case. But if I start the year on January 1st and I already have 500 cancer cases in this city, imaginary city, these 500 cases are prevalent cases. They already occur in the past, they're already the existing cases. And each one of the new ones, they're going to count for incidence, the new ones, but they also count as prevalent cases at the end of the year 2004. So if a disease occurs like diabetes, they usually don't die within a year of diabetes. You diagnose as diabetes. 500 people diagnosed with diabetes until December of 2023. Comes January 1st, 2024, I have those 500 diabetic people still alive. And then I start observing another 10,000 people in this population, and 1,000 of them develop diabetes. So by the end of 2024, I'll have 1,000 new cases plus the existing old cases, 500. So I have 1,500 prevalent cases. So prevalence makes no distinction between incident cases, which is new case only, or any cases, all the cases. Now that's your prevalence. The denominator is very similar to the risk. Okay, it's identical. It's the population on average. For surveillance purpose, the denominator is the same. For study of a cohort study, it's a little different because you need to make sure that all of them are population at risk in the incidence calculation and the cumulative incidence or risk. Whereas in prevalence, you are not concerned about that. Okay? So it's just a proportion, folks. Prevalence is the number of existing cases in a population during a defined period. Incidence is the number of new cases. Remember, for that population, and these cases have to be all at risk. So there's a little difference, but they look alike. Indicates the number of existing things out of the total population. It varies from 0 to 1. It's a proportion. Measure either at a point in time over a short period of time. It's called, that's a silly distinction. People should never care to worry about that. Point prevalence or period prevalence, doesn't matter. Okay. So include prior cases, existing case, surviving case if it's a chronic disease doesn't kill you. It's not a true rate, it's just a proportion. And it can be called all those things you see here. Now, it's remembered that the prevalence is a function of both the incidence and duration. Why? Think intuitively. I gave the example of 500 people with diabetes in year 2003 in a city of 10,000 people. And then in year 2024, another 1,000 developed diabetes. So I end up, by the end of 2004, with 1,500 cases or 1,500 cases of diabetes out of 10,000 people in the population. That's your total prevalence by the end of 2024. 1,500 diabetic cases divided by 10,000 people in the population by the end of 2004. So what fed into the numerator of this calculation of this prevalence? The duration of the disease, right? Because it was diabetes, 500 cases in December, they're always going to be diabetic by December 2024, unless there was an exceptional case, 1 of 10,000 people with diabetes had a reversal of diabetes because of perfect lifestyle modification, and the guy was 100 kilograms and now is 50 kilograms in 5 months. Yeah, it's possible to revert that, but that's very rare. Usually, if you have diabetes, you continue. So duration of the disease contributes to the total number of prevalent cases in the numerator. The longer the duration of disease, the more prevalent the case become. HIV/AIDS, before treatment was possible, okay? First 6 years of the epidemic, you got diagnosed and people say, bye. You died within 6 months, right? So that's a very short duration of disease. So that did not contribute to prevalence. You have incredible increase in incidence of cases with prevalence not changing at all. Because every year there will be diagnosed new people, almost every one of them will die in that same year. So they don't accumulate to the next year. So duration of disease matter. Whereas diabetes, I'm diagnosed today, likely in 5 years I'll still be diabetic. I'm contributing to the prevalence every year. The other thing that contributes is the incidence itself. If the disease has a power of morbidity, that means it causes new cases to accumulate more cases. It's the case of HIV after the treatment. After the treatment, the disease became what? Curable, right? Now you have people 35, 40 years of HIV/AIDS. And they're not dying. They're still alive. So duration make them live. But the incidence is still there. It was very high. It was 0 before the epidemic started. And all of a sudden you have new cases coming in, so they contribute to the total prevalence. So the total prevalence is huge now of HIV/AIDS cases. Actually, I would say HIV infected, because the AIDS disease is controlled by the medication. Okay? So for a state, so you can present prevalence in many ways. For a statewide survey, 1996 in the state of Missouri, this is a survey I did. 6% of the population at that point in time were diagnosed with diabetes. Do you know what the number is now? Any guess? Fred, can you guess how many people? This is 1996. I was the state epidemiologist in the state of Missouri in 1996. So what do you think is the prevalence now?
It's higher. Is it higher?
Good, it's higher. But how much higher? Can you guess?
At least double the numbers.
You got it right. That's a little bit more than that. It's triple. It's 18%. Here's the prevalence presented. So you usually present prevalence in graphs like that, a histogram or kind of a bar graph or something. For instance, this is the prevalence of diabetes in Missouri in 1996 by their race. Because race is a mark of other things. It's not the race itself. So you have African Americans, you have white, you have the total population, the dark blue. The light blue is the white. It didn't matter which city you went. However, there was one special place, Boot Hill, where the prevalence is huge. It was already 18.3%. That's what it is now for the total population. For the total population of the state, I don't show it here, but it was about that number that I gave before. Can I go back? No, it doesn't want to go back. It's okay. Prevalence of diabetes by education. You can see the education matter. The more educated you are, you have more uptake in information, and you educate yourself, you tend to do the best things for yourself. The more you're educated, the more knowledge you have, the more care you take care of yourself. Not surprisingly, you have highly educated people doing a little bit better. Those who have less than a high school education doing the worst. Didn't matter what, even the race, they're still higher, nearly twice or 3 times higher than the other group. The prevalence is very similar. The standard error of the prevalence. Remember, the risk was risk, then multiply 1 minus risk, divide by n, square root. Risk is a proportion. Prevalence is a p. So it's p multiply 1 minus p. Why? Because the variance of any proportion is pq over n, right? And you square root of it, you have your standard deviation. For the total population is n minus 1, it's going to get the standard error, which for large numbers, the n minus 1 make no little difference. Okay? 1 minus f if you're in a territory that you need to adjust for sampling or something. So where, again, this is all reminder, that's why I'm going fast, folks. So the prevalence, you calculate the confidence interval, you calculate the standard error before here, and once you have that number calculated, say your prevalence is 0.3. So it's 0.3, then multiply 1 minus 0.3, which is 0.7. So it's 0.21 divided by 10. That's your sample. So it's become what? 0.021, right? So that's your standard error. And you multiply that in the next step by 1.96. So that's a distribution of all possible p's. In a standardized, normalized distribution, you got 1.96 multiplied by standard error. That's going to give you the plus or minus to your confidence, how confident you are that your prevalence was actually 0.3. Example here, I have a P of, C is 10 out of 100 people, or P, I think I call P, I put the name C just for you not to get worried about terminology and acronyms and stuff. What matters is that this is the event of my interest. That's my prevalent cases. 10 cases out of 100 people being observed over a year or a month or a week, whatever. So you got a 10% prevalence estimate. So it's 0.1, then multiply 1 minus 0.1 divided by 100. That's your standard error, okay? And then you got your P, which is 0.1, 1.96 to multiply by the standard error, which is 0.030. It's going to get this plus or minus here. That's your confidence interval. You're confident that this prevalence is either 10% or at least 4%, maximum 15.8% or 16%. Notice that's a very wide confidence interval, and you should learn that from your basic statistics because your N is too small. It's only 100 people for a very rare event, 10%. That percentage was a little different, maybe your numbers would be better. But also if you have 200 people, this confidence interval will be tighter. If you have 1,000 people, this confidence interval likely is going to be somewhere between 0.7, 0.7, and 0.12. Here's an example, both prevalence and risk. Okay, I know looks a very complicated table. Okay, but here you have cohort study, short follow-up period, risk of disease overall, and risk of disease among exposed to a risk factor. Okay, so you have your sample, 74,000 people. You have proportion of disease, proportion exposed. So it's coming out of that table here. This table 7.4, you see that? That's your study one, risk factor positive, first column, risk factor negative, second column, risk, 1 minus risk. So if I'm calculating a prevalence and a risk, numerically they look like the same here. Because I can, it's just to confuse you actually. I'm doing that on purpose. But they are different animals. One is the risk interpretation. It's about what is at risk. If the people denominator are all at risk, then I can estimate risk the same way I estimate the prevalence. But if I need to extract some of those 74,000, let's say I'm talking about infectious disease here, and I'm talking about measles, I need to make sure I remove all the people who have been immunized or had measles when they're kids. Okay, let's say 5,000 people. Then the risk and the prevalence will be a different number. Because for the risk, it would be 69,000 people instead of 74,000 people. Just wanted to be aware of those things and how to calculate confidence interval. It's about the same. Okay, very similarly, except that the risk here is actually a little different because the way it came out. Risk, look in each column, on each row, look the same, but when you calculate that here, given the numbers we have, do your homework and ask me tomorrow. Send an email to me. Make sure you are there in the YouTube or internet watching this lecture. Send an email to me why the risk is this value is 0.3, prevalence is 0.25. Okay? Then you have the calculation. The formula is very similar. Just substitute R for P or P for R. You're going to get the same formula. But because the initial number is slightly different, one is 0.25, the other is 0.30. Here's the proportion. Okay? Proportion of disease in the exposed, proportion of exposed, proportion of exposed, proportion of disease. So proportion of disease is 0.25. Okay? So you have risk factor. Here's disease positive, is first row. Disease negative, second row. Okay. So that's what you got your number. There are 18 by 500 divided by 74,000. It's going to give you the prevalence. Whereas the risk is going to be new cases.
Professor, take care of the microphone.
Oh, tem que falar no microfone. Desculpe, pessoal, estou um pouco longe do microfone, mas eu soube, ele falou que isso aqui também está
You can use this one, but close to the mouth.
Oh, eu tenho que falar. Fica difícil, quando a gente tem que mostrar.
Yes.
Dá para ouvir agora lá? Mas não está ouvindo nada que ele está mostrando para eles? Deu para ouvir alguma coisa? Eu quero que vocês, alunos aí à distância, olhem essa tabela aqui e descubram por que o risco é 0,30 e a prevalência é 0,25, 0.25. Did a little bit of Portuguese, so not to confuse you. So now you have the confidence of our calculation is about the same in terms of the formula. Is P that multiply 1 minus P, P that multiply 1 minus P. Okay? Here. And you square root this whole quantity. Actually, the formula is wrong here. That's okay. So how is the prevalence affected? I already gave plenty of examples. We're going to take a short break. We're going to go back to foundations of these measures, just give it to you, prevalence and risk. I'm going to add the foundation for odds, so you understand where they're coming from, why they're coming from. And then we end up talking about incidence rate, which is the main measure in epidemiology, the fundamental measure in epidemiology. Take a break of about 15 minutes. Thank you all.
Você fica falando que realmente você estava fora do som.
Ele disse que deu para ouvir. Longe, mas deu para ouvir. Ele disse que deu para ouvir.
Ok, tá bom, pessoal. Tô ouvindo daqui. Ok.
Tá todo mundo ouvindo.
Não, é que ele se distanciou, falando baixo, olhando.
Quando eu tenho que mostrar, tem que estar aqui. Eu pensei que captava aqui, eles têm que falar perto.
É que eles são unidirecionais. E a direção capta quando você está direcionado para ele. É
Difícil.
Sim. Dá uma pausa?
Dá uma pausa lá. 15 minutos.
We are back.
Okay. So welcome back, everybody. We're going to continue our conversation, doing a little review on the statistical foundation. I hope to spend another 30 minutes on this, and we're going to move into probably the last topic. We can review some of the stuff at the end if we allow the time. But I just want to remind that this material I'm presenting today, all of that's going to be available to you. And this one specifically on statistical foundation, I want you to use it as a resource. I want you to read about it and ask a question tomorrow, send an email. That is send an email. Go exactly to where the presentation is and make sure that you have the right answer. Here we're going to just brush through it. There's 80 some slides. A lot of that is copied from notes, old notes I had that I want you to read. So it's not really to present as a lecture. I'm going to present a few vignettes of this whole material here on the statistical foundation. Okay, so bear with me. So we're going to talk about three major distributions in statistics: the binomial distribution, the Poisson distribution, the hypergeometric distribution. You should have had that information in earlier courses that you've taken, basic epidemiology or basic statistics. But we never know. It's good to refresh a little bit. What do they mean? How do they relate to the measures that we use in epidemiology? And these measures that is mostly associated with the studies like case control studies, cohort studies, cross-sectional surveys. They're actually fundamental measure for all the big studies we're going to look at starting tomorrow, halfway through the lectures tomorrow, and the next few days. Going to be focused on how to evaluate interventions. And those major designs use those principles, use some of those measures, especially the clinical trials. In the clinical trials, the incidence rate and the risk are the fundamental measures are still on clinical trials in general, okay? So in a cohort study, I could present the study, a typical epidemiological cohort, into two groups that I'm following up over time. We're going to see that later in another lecture tomorrow. We're going to be focused on this, actually. But I want to give you the foundation for that, so I'm anticipating some discussion. So in a cohort study, usually you have exposed people and unexposed folks that you follow up over time. That's your traditional cohort. So Serdon and Hill and tobacco and lung cancer back in 1950s, 1948 through 1954, 56, around that time, they follow up thousands of physicians in England. Why? Because they have incredible registry of the physicians. So every time a physician become a physician, they are registered, and they follow these people up until they die. And if they die, they are taken off the registry with a mark saying you're dead. Okay? And if you're ill and not practicing, they also take you off, and they tell how many, how many months or years you're off because you're ill. Not dead yet, but ill. So all this information allowed them to say, okay, well, what if I follow people up and find out how many would die, how many would develop some disease and disappear from the follow-up period, right? So they did a study in which they follow people who are exposed to what? Tobacco. They asked 3 quick questions. Do you smoke? Yes or no? What kind of smoke you do? Is that pipe? Is that a cigarette? Is that a cigar? Okay. And then later on, they say, how long have you been smoking? And how much do you smoke every day? And they have some measurement, more or less, to figure it out. So these are the general questions for the study, and they follow people up. And later on, out of the exposed people, they found out X number of people developed what? Cardiovascular disease. Ischemic heart disease, most important one. And out of that, many people follow up, X number developed lung cancer and chronic obstructive pulmonary disease. So they are the fundamental studies that gave rise to the knowledge that we have today that say, hey, you should not smoke. So by 1964, after these incredible studies done in the late 50s with data that initiated the follow-up in the 40s, right post-war II in England, then they established the association. So this is a traditional cohort. And I can present any cohort in that way. You have A plus C exposed people and B plus D unexposed people. So out of those A plus C people, how many develop the condition? And out of those people who are unexposed, how many develop the condition? So I end up with the risk ratios, okay? Actually, there's a typo here. The top one, disease minus, should be disease plus, and the bottom one should be disease minus. I don't know why. I was too distracted. Just for presentation, it could be that way, but you wanted to go R1 divided by R2, not R2 divided by R1, okay? So in that way, the risk ratio or the relative risk, the risk in one group divided by the risk in the other group, it's produced in the right way. So usually that's the way you present count data, the count data on a cohort study. Later on, you're gonna learn tomorrow. I'm gonna go in depth into this issue. So don't worry too much about it. So count data means I'm worried about the counts, how many people. The other way to present cohort data is to person years data. So I don't have the bottom C and D. I have A plus B cases, diseased people, and then PT1, which is person time of the first exposed group, which is a summation across all people being followed up for all their time that they provided to the follow-up. And the same thing with the unexposed group. So that's another data presentation, okay? We're gonna talk about that later on. So this table here follows magically some statistical theoretical distribution. That distribution is binomial. And a binomial distribution is a distribution that has an expectation for what's the event of my interest happening, what's the expectation of the average happening of this event is n minus multiplied by p, which is the proportion, the probability of the event occurring multiplied by the number of samples that I have in my hand. That's my little n here. So NP is the number of things, okay? So the expectation for X, in this case, NP, okay? So be the expectation for A, for the cell A. There'll be some form of NP. The variance of that X is going to be NPQ, N that multiply P that multiply 1 minus P. Q is just another way to say 1 minus P, probabilistically, okay? So that's your binomial setup. In a binomial distribution, you have two potential outcomes of interest, success or failure, yes or no, disease or not disease. Out of the exposed group, I have some developed disease, some did not. Out of the unexposed group, some developed disease, some did not. So two binomial. Each column is a binomial. First column is a binomial of exposed people. The second column is a binomial with n equal A plus C, the total n. And the P is A divided by A plus C. That's P1. And P2 is B divided by B plus D. That's P2. And if I divide this P1 by this P2, that's a risk in one group divided by the risk in the other group. That's your risk. P is actually R. Risk, right? Same thing. Probability of success is the same across all trials. This is assumption. That means if I do create tables like that out of population in general, I create different cohort, the probability of success is the same. There's a phenomenon occurring in the population that I'm not modifying it because I'm randomly sample. Is going to reflect that. Let's say the chance, the probability of thyroid cancer in a population of São Paulo is 1 in 10,000. So if I take a random sample of 1,000 people, I should expect one case to be thyroid cancer. If I take another random sample, another 1,000 people, I should expect one case. So the probability did not change, it's the same. I'm just doing different experiments. So that's what they say, probability of success the same across all trials. Every time you take a random sample, you end up with this, same probability. Number of tries fixed, that's the number of times I'm trying to estimate the P, it's N. Each try is identical and independent. For example, if I say diabetes affects approximately 10% of the population, in a random sample of 10 adults, what's the chance that one of them becomes diabetic? You are in the binomial territory. I know what the probability of happening on average because somebody's study gave it to me. It's 10%. I want a sample of 10 people only. I took random sample of 10 people in the population in general. And I try to go and measure their glucose level early in the morning after they stay 8 hours, ideally 12 hours without eating anything. So that's my establishment. Say if the glucose is above some level, 110, I say you're diabetic or pre-diabetic. Okay, so that's my definition. So I go after that little example. So the probability, this probability, say, what's the probability? I already know it's 10% follows a binomial distribution. Another example, flipping a coin. That's what the usual statistician uses. I use already the disease as an example. Every time you flip the coin, you have a 0.5 chance of obtaining heads or tails. Number of tries fixed is every time you do, if you do 100 times, it's 100 times. Every time you do, it's one fixed value. The probability of head equals success is the same across all trials. Each trial is identical and independent, meaning when I do toss the coin, flip the coin one time, and I flip a second time, the second time is not affected by the way I did the first one. They're independent. So when I take a random sample of the population, I take another random sample, they're independent. Now, if the population is very small, and I take, let's say, a population of 100 people, I take a random sample of 30 people, I only have left 70. That's a small sample. If I take another sample, it's going to affect the probability will be different. That's a different territory. We're going to talk about that hypergeometric distribution. It's like simply without replacement or with replacement. It's a lot important for when you're dealing with other things. But usually talking about large population, it doesn't affect. So binomial example, I'm going to give you an example. A random sample of 10 adults in a population. What's the chance that one person among them have diabetes? I know that the probability is 10%. So I should expect that's the most likely thing to happen is one case to be diabetic, right? But what exactly is this probability? In each trial, the probability is 10%. Number of tries fixed. I'm going to do 10 people. Every time I take one person, it's like a trial. So my trial is fixed trial, 10 people. Each person is the trial in itself. Each trial is identical, independent. They're independent people. I'm randomly sampling them, so they're independent. So if I throw that in Excel, I call binomial distribution 0, 10. That's my trial, number of trial. That's a sample of 10. And 0.1 is my probability of success. And I say false. And I type this exact that in Excel. It's going to calculate this for you and say, this is the probability distribution based on a binomial. These are the possible values in a binomial. Out of 10 people, you could have 0% with no diabetes. You could have 1 person with diabetes, 2 persons with diabetes, 3, so on and so forth, until 9 people. Because these are the probability. You got it? So you get 10 people, right? So I have 10 possible values for X. That's your expected value for X. What's the expected value of number of cases of diabetes? Remember, X is not the proportion. X here is the number of cases with diabetes. The P is the probability. It's 10%, 0.10. Okay? So Excel gives you that. You can see the distribution here that you say, well, I'm going to bet that it's going to be 4 cases. Out of 10, 4 is going to be diabetic. Very little chance. And if I do sample randomly over and over, I'm going to get 4 only how many times? 0.01. It's less than 1 in 1,000. It's about 1 in 1,000 times. Okay? On the other hand, what's the most likely probability? It's 1 because the P is 10%. So 1 is 10% of 10, right? So the higher probability, 0.39%, is for X to be a 1. So again, the experiment is I take a random sample of 10 people. I know the prior probability, if I'm looking at Bayes' theorem, the prior probability is 10%. So what are the odds? What are the probability that my first case is not diabetic? That's a different story. But say out of the 10, I'll have a 0 diabetic. Out of 10, I'll have 1 diabetic. Out of 10, I have 2 diabetic. That's called probability distribution. Okay? And that's what Excel gives it to you. Well, that's what regulates what you do with the risk factors and disease in a cohort study. You're looking at each column exposed to tobacco, unexposed tobacco. Each column, it's a binomial distribution. And if there are N1 people there in that column, that's your denominator. That's your denominator. He said that even when I talk out, it's picking up. Even when I was talking here, it's okay. So binomial, you can say the first step in a binomial. I'll skip that, but pay attention to this. I'm basically deriving from Bernoulli trial which is a slightly different thing, but it's the precursor of the binomial. And I say, given some circumstance, the Bernoulli trial is going to give you the expected value of the binomial and the variance of the binomial. Just read about it. There's something else called the binomial distribution formula. I want you to be aware of that too, and how that comes about. But more importantly, you have the formula is p to the power of y, 1 minus p, n minus y, when y is your event, or could be x. Sometimes we call y, sometimes we call x, okay? Sorry for the confusion. But I wanted to, sometimes I do that on purpose because many books comes I, y, x, doesn't matter. How long you understand, p is all of the proportion, the probability based on a binomial. And n choose y, and that you need to have here, n choose y. Remember that from analysis, combinatorial analysis, basic math. Okay, you have the formula here for n choose y. Okay, p elevated to y, 1 minus p, the elevated to the power of n minus y. That's your famous binomial distribution formula. You have the way to calculate the confidence interval, and you have something called large sample approximation, and it's very much used when I do the confidence intervals for you. I'm taking the original binomial formula and simplify with a large sample approximation. All these are large sample approximations. I'm assuming that your sample is large enough so that the binomial approximate a normal distribution in terms of standard error. So the other table I mentioned to you before from cohort studies, the density table. Instead of A, B, C, D, I have A, B, and then PT1 and PT2. That's the number of years of observation, number of person time observation for the exposed group of people and the unexposed group of people. That one doesn't follow a distribution called binomial. It follows a Poisson distribution. And a Poisson distribution is a distribution function for rare events. My dad used to do something interesting. He would stay on the corner of the street sometime and he'd say, do you want to bet that the next car that comes out is going to be a car the color red? And I say, how much you want to bet? And we always nervous because he was very good at probability. And he always won. But that's a Poisson distribution because it's such a rare event. Well, the next car to turn the curve on a corner that you see it's a red car, color red. How do you know that, right? That's a Poisson distribution. It's a rare event. Or something that happened very rarely, like the incidence of cancer, rare cancers happening over a time period in a large population. That's a Poisson event. So here you have a Poisson distribution. Every time you're in a territory doing a cohort study and you look at the person years of observation. Because if you have 10 years of follow-up of 100 people, even though N is very small, 100, right? But it's 10 years follow-up. And if my follow-up is person month, so I have 12 multiplied by 10. I have 120 months. And I have 100 people. Let's say every one of them contribute the whole 120 months. So I have 100 by 120 months. I have what? 12,000 person month of observation period. That's a very large. So your denominator is very large. Your numerator is very small relative to that because I'm looking at how many cases are going to occur in these 100 people of a rare thing like cancer. You follow that now? Person years, you're going to learn that tomorrow very carefully, how you estimate the person years. Actually, maybe in the next lecture, I already give you something. But anyhow, you're in a territory called Poisson distribution territory, where the expectation of X is no longer NP, like expectation for the binomial event. So the expectation for this A here in the count data for the cohort study is NP. It's your sample that multiplied by the proportion. I take a sample of 10% of a population of 100. The probability of diabetes was 10%. So it's 10 out of 100 people multiplied by 10 divided by 100, which is 0.1. So that's my NP for binomial. Here it's different. It's called mu. That's it. You're going to estimate the expected value of mu. And mu is a function of the incidence rate, which is the incidence rate density. You're going to learn that later, but I want to give an anticipation of that. And the variance of that X is mu also, meaning the expectation, the mean, and the variance are the same. in a Poisson distribution. If you have violation of that, when you're doing that later on, I'm going to talk about, in the last lecture, he's going to be about meta-analysis, going to see formulas that actually emulates a little bit of that, because we're talking about Poisson territory. But in there, sometimes these assumptions don't hold. The expectation for the value of X and the variance of X are not exactly the same like a Poisson expect, because the variance becomes very large, is spread out as the value of X change. So in that case, you have a territory called negative binomial. I'm not going to cover here, but that's the formula is different. And you estimate that if you use SAS or Stata or any of the statistical software, you need to say, hey, my statistical distribution is not a Poisson, it's a negative binomial. Okay? You should calculate an incidence rate in a regression based on negative binomial. So the formula for the Poisson is E elevated to the minus lambda multiplied by quantity lambda multiplied by X, or not multiply, exponentiated to the level of X factorial as your denominator. Okay? So formula sometimes also read as E to the minus mu to the elevated to the X, and X a factorial. Because sometimes those two things are used interchangeably depending on the book in epidemiology and statistics. So they are all discrete distributions like the binomial, but at a different type. And the lambda is always greater than 0, but less than infinity. But I can go to infinity. For Poisson distribution, the mean and the variance are always the same. So these are the general assumptions about this distribution. So if you have an event like cancer, I told you this there, describe the number of events occurring in a fixed time interval. It's called so-called region of opportunity for that event to occur. Usually in a Poisson, you're looking at time windows, expectation over time. How many cases are going to happen in 1 year, 2 years, 3 years? That's a Poisson territory, especially if the event is a rare event like cancer. So how many new cases of cancer occur in 1 year in Callaway County? This is me. Callaway County is a county in Missouri, the state of Missouri. How many new cases of severe restrictive respiratory disease occur in 1 year in a popcorn factor 120 workers? Both or Poisson distribution probability that I use in studies. We're going to look at an example at the end of this course. I'm going to give you two studies that I did. This one here, the second one, I use a Poisson distribution to say this could not have happened by chance alone. It's so rare. And what's causing it is a new thing. It's a new disease. It's a new thing, a new risk factor. And now there's a law in the United States that prohibits that thing to come in contact with your food. And yours here is the one that discovered that, and I'm very happy for it. There's a lot of people with me on that. You can see in the paper. But the Poisson distribution for a lambda of 4 is this beautiful distribution. So the most likely event is a 4 or even a close one to 3. It's very close. But the other events say, oh, I should see 8 of such event. Well, the probability is way too small for 8 or 9 or 10 event. Whereas for 3 and 4 is almost the same, it's very high. So likely the next event is going to happen at the level of 4. I will have 4 cancer cases occurring in this population over time. So Poisson assumption, rate event occurring constant across time intervals. Probability of one event does affect the probability of the next. Does not. Sorry, does not affect. Sorry for that. Events are independent. Need to check assumption. The PMF, the so-called probability mass function, which is probability distribution of 5 of the events being 5 instead of 4. When the mean is 4, then apply the formula. Remember the formula I gave it to you before? And you can get that too. You can say to Excel, Poisson dot dist, put the value 4 and 4, 5 and 4 false. It's going to give you that probability. So basically here, I'm asking Excel to calculate to me, what's the probability of getting 5 cases of cancer in a probability mass function that the lambda is actually 4? That's the most likely event. I still want to know what's the probability of a 5. So it's giving me a 15.6% chance. Okay? Here's the probability that you can find. That's another use of the formula where X is a random variable, blah, blah, blah. You can calculate probability for anything. What's the probability of getting a 0? it's E, using that formula is E to elevate to the minus mu, and so on and so forth. You can calculate that. You should have had that on basic statistics. Consider Poisson with mu equal 3 or lambda equal 3. What P is, what's the probability of obtaining a P of 2 or number greater than 2? So you calculate the probability of greater than 2. That's this big here. And then you take 1 minus that, you calculate the probability, what we asked before. You can look it over. I gave all the examples here. You can look at it. Just look for that, okay? It's yours. There's a lot of material in this lecture that I'm not going to cover. It's just going to mention to you so you know these distribution, Poisson, and binomial, they underline what you calculate. That's why the confidence intervals come like that. In a case control, you have a little different situation. You have, let's say you have a traditional cohort studies, an underlying cohort, but you want to do a case control out of that cohort, okay? And all your cases versus control are incident cases. While in a territory of so-called hypergeometric distribution, okay? You have little n, that's your sample, your little n, your cases, okay? Total n is the total population, and A is the expectation of your exposure group, okay? So you're in a hypergeometric distribution with expectation for X, the value of A. What's the value of the cell A should be? That's N multiplied, big N multiplied by N, and so on and so forth. I'll explain what these terms are. So the formula for the hypergeometric is Kx, N minus K, N minus X, big N, and little n. So basically say K choose X. I don't have the way in to do the formula. Remember the combinatorial analysis? K choose X. Remember? Arranjos, combinação, permutações. Okay? So that's what we're talking about. K choose X. N minus K choose N minus X. And N choose N. Okay? Once you have that, that's your hypergeometric distribution formula. It's equivalent to the binomial, but without replacement. So in a binomial, I am assuming when I take a random sample and I take a second random sample of the population, they are independent sampling because the population is large enough. And one trial does not affect the probability in the next trial. But here, if you have a situation where if I take something is missing, it's going to affect my probability, that's a hypergeometric distribution. It's like sampling without replacement, okay? So probability of success changes with each draw. By the way, by that description I just gave it to you, know that if I have an n large enough, the hypergeometric becomes a binomial. Because even if I sample any number of people, it's large enough, that's not going to affect the next probability. Maybe by the 20th decimal place, it will be affected, but not in a big number. So probability of success changes with each draw. Because of this, it's affected by the lack of replacement. So total.
How large enough? So when we have this distribution large enough, how do you have a number?
Yeah, we do. Usually, case control studies, for instance. Okay, you're dealing with a finite number of cases and controls. It's very expensive to do studies like that, okay? So in that situation, the hypergeometric is the right idea for you because we're talking about 200 cases, 600, 500 controls, 1,000 cases, 300 controls, 40 cases, 180, 120 controls, 80 controls, 40 cases, 40 controls. So we talk about a small number. We talk about thousands and thousands. Then the hypergeometric or binomial will do the same job on that mathematics, on that statistics, okay? I'm going to show that to you later on. A good question, Leonardo. So probability of success change with each draw. So this is a card, playing poker. Again, never play against the old man. He was good. He will beat anybody in card because he count the numbers. He knew exactly what the hypergeometric probabilities are. Defined by three parameters, big N, K, and N. Big N is the total population. So in this case of playing poker, there's 52 cards in a deck, right? So K is the total items of interest. Say I'm interested in spades, espadas, right? all the cards are spades. There are 13 spades there. And the sample size is, what's my hand? Usually it's 5, right? I receive 5 cards. The other person received 5 cards, right? That's my hand. That's my sample. That's my random sample. See how small is the sample? Is 5. That's my hand. So out of 50 cards, I got a hand of 5. How many are spades? That's a question, right? You apply the hypergeometric distribution. So I'm saying this is the formula, recall. So in sample size, I'm going to do the distribution. So now I know that the probability of obtaining a zero spade, no spades, is about 0.22%. I mean, 22%, 0.22. The probability of obtaining one spade, at least one spade, 0.4 and 0.42 or 42%. The lowest probability is a 4 here. 5 is 0 probability, okay? I mean, the probability of getting a 5 out of 13 spades, getting 5 spades in a hand of 5 out of 52 cards is 0. So the only thing that could happen is 0, 1, 2, 3, and 4. You see how that goes? That's your hypergeometric distribution. I want you all to read this. This is more examples, more ideas about what do you mean by that, okay? In factorial, n minus k factorial, n pk. So n pk is n choose k, is the permutation. Remember permutation? That's what it is. But read it. If you have a question, you can send an email. I just wanted to give it to you. It has the whole theory here with some writing from an old professor of mine from Emory University nearly 35 years ago. Odds ratio, that's another measure we're going to use it. Where is it coming from? From the hypergeometric distribution, from the case control studies, right? So here's how to estimate odds. We're going to skip because I'm going to show something more interesting about odds ratio. I want you to start. So can an exposure odds ratio estimate the risk odds ratio? Okay, we're going to see that tomorrow when we do the case control, when you do the cohort. I'll show you better graphic, better tables. This is just kind of drafty, rascunho. So it's a lot of not so good. So you have notes, you can read it. We're going to skip it because that's not the main purpose of the lecture. It's just a refresher. So it depends what you're selecting. Hypergeometric, RV, random variable can become a binomial. Yes, it can if the n is too large. Can a binomial becomes a Poisson? Yes, if the event is too rare and the n is too large, then the NP becomes lambda, the Poisson. Risk estimate and incidence rate, are they the same? No, they're different animals. One is come from binomial and other from Poisson. But given some circumstances, they give you the same value. What's that circumstance? Again, when the binomial is too large, I told you binomial, right? When the n is too large and the p is very small in the binomial approximates the Poisson, the risk becomes the incidence rate and vice versa. It's one measure, but for small numbers in a traditional cohort study, an epidemiological study of causation of disease, no, they are different things. They give you different numbers. But for large populations, they're going to give you the same. Remember how the risk is calculated? New cases divided by population at risk over a period of time. Whereas the incidence rate I'm going to show you next is the new case, exactly the same numerator, nearly the same denominator, population at risk. But I'm not interested in the size of the population. I'm interested in the observation time of that population. How many person years of observation, person month, or person days, or person weeks of observation. Each person in that group is given to me. And the summation across those, that's your denominator. That's what makes the difference become very large in that number. So the event happening is rare already, but the denominator is very large. You got a Poisson situation. But if the binomial is coming out of a very large, 10,000 people, and I have a rare case of cancer, that risk estimation and the incidence rate will be the same value. 0.01 will be identical. Okay, I'm going to show it to you that quickly. And what do different case control design estimates depend? If you have a case control of incident cases, the odds ratio estimate something different than you have prevalent cases. So you have exposure odds ratios, you have disease odds ratio, you have prevalence odds ratios coming from a cross-sectional study. Here's a little bit of what I told you. As n approximates infinity, become very large, the binomial approximates, the hypergeometric becomes a binomial. Okay? Here's the whole piñata. I'm not going to go over this. The other hand, if a binomial approximates a Poisson, what are the conditions when p becomes very small, the proportion becomes close to 0 as possible, and n is very going towards infinity, your binomial becomes a Poisson. So your NP and your lambda becomes the same. And that's why in large population, if you estimate the risk in a city of Columbia, Missouri, where I live, 110,000 people, what are the number of thyroid cancer cases? The incidence rate of thyroid cancer cases is going to be exactly the same as the risk. But if I have a small number of people I'm observing, 500 people observing over a 5-year period, the incidence rate is going to be very different than the risk, which is the cumulative incidence. Okay? Just read this. I give it to you. And can risk and incidence rate be related? Yeah, they are related. They're cousins, like I told you, right? When the cousins are too close and look at each other, they're almost identical. So risk equals to 1 minus exponential of this value here, which is an estimation of your rate multiplied by time. That's your event multiplied by time. That's your rate. Okay? So when you do that, you can find out that the two are related. So incidence rates, okay, like 0.08, 0.04, 0.02, 0.01 becomes yield in that formula, these values here. I want you to read about it, what that means. When the limit of that, you can look at that. Remember your old algebra stuff. So you can come up with risk estimation from the incidence and vice versa. From the risk, it goes to the incidence. Okay? This is a quick and dirty formula. You got 1 minus exponentiation of your minus incidence rate multiply actually equal time by time. Okay? So, or simplification, if t is very small, your time period is very small, you just have I that multiply the time. So the incidence rate and the risk is just one estimates the other. So I wanted to give you that so you know there's a relationship between them. Likewise, there's also a relationship between incidence and prevalence. I told you that the prevalence gets bigger if the incidence rate is higher or if the duration of disease is very large. When both are very large, you're going to have huge incidence. So they have to be related. The simplified formula is just P, prevalence, is the incidence multiplied by the average duration of the disease across the population. So if diabetes lasts a lifetime, usually diagnosed in your 40s to 50s, usually. Some people earlier, some people later, but usually it's getting close to your 50s diagnosed with diabetes. You're going to last another 20 years because it's shortening your lifetime. You're going to develop a lot of other things. So the average duration will be about 20 years, right? For all diabetic person. And you have the incidence of diabetes multiplied by the duration, you get an estimation of the prevalence. And likewise, you can do by, you know, that P over D is going to give you the incidence. If you have the duration of disease and the prevalence in the population, divide one by the other, you're going to get an estimation of the incidence. And like I told you, I will leave that for tomorrow, the exposure odds ratio, risk odds ratio, because this is too drafty. And tomorrow I'll show better tables for you. So let's stop here and go back to the lecture on incidence rate. I'm going to give you, I think we will be on for 30 minutes right now. Okay, so let's go to the incidence rate measure. We're going to stop halfway through and then take a quick break and finish if needed. But likely we can finish in 45 minutes, 50. You guys got 10 minutes free. Not worry about anything. Yeah, that's what I'm saying. So we learned about prevalence, we learned about cumulative incidence of risk, and then we learned a little bit the foundational science of that, which is statistics. And what are the statistical distribution underlying those measurements in epidemiology? Tomorrow, you're going to learn how each measure of disease occurrence can be modified to become a measure of association, because I'm talking about measure of incidence or disease occurrence in one group, in measure of disease occurrence in another group, the exposed and unexposed to risk factors. And that way you correlate them. Okay, you correlate the risk factor with the outcome, with the disease. So the incidence rate is the fundamental measure in epidemiology. We think that. Okay, so let's go to, well, once you go through, to come back is impossible. No, it's not coming back. I want to see. That's okay. I wanted to return, but that's okay. So again, the incidence rate is like the risk, is an incidence. Remember, the risk is also called cumulative incidence or risk. Here you have the true rate, or the incidence density incidence rate. Okay, numerator is always the number of new cases arising from a population at risk, like the risk. Denominator is the sum of time each person at risk is observed over that period of time. Totally across all people being observed. Okay, so it's number of new cases of disease or injury during the observation period, multiplied by 10 to the power of n, whatever, 10, 100, 1,000, divided by time each person was observed, total for all persons. So you sum up all the person times of observation of everybody. Like risk, reflect new cases, how it's a true rate and risk is not. Type of incidence that directly incorporate time into the denominator by the observed time each person provides to the follow-up period. The denominator measures person time units. How do you go about measuring that person time units? You need to have some rule. If a person is lost during the follow-up period, you have to find a way to adjust for that. Usually you give half of the period of observation as the amount of time that person is observed, because I lost that person. So I don't know when I lost that person. And that's why doing evaluations of interventions over time, don't wait too long to do new measurement. Do more often, because you don't know what's happening between. And if you have lots of loss to follow up, you may make a mistake in assuming that each person have half of the year. Okay, it's a good guess. Okay, but you never know. If the numbers are small, this good guess could be very wrong. And you get incidence rate which are miscalculated. Okay. Here is the same example I gave you before. Okay. And you can always follow people over time and count how many months of observation or weeks of observation each person gave. Let's say month. October 1st start here, and you have 1 month, 2, 3, 4, 5. And you're in April already. So you got November, December, January, February, March, you start April. Okay? So you have 4 months here at the bottom. So that's your follow-up time is from October 1st to September 2. That's 12 months. So in 12-month period, this person here, so date of death, date of onset of disease, date of recovery. So if I'm doing a follow-up for the disease occurrence, I cannot include those that already had the condition before the follow-up period starts. So I eliminate them. Those 6 people are gone. So I'm going to say anybody else new that comes in place and develops out of those that I was observing, they're going to be my case. I gave some example here. Why did I write it there? 10 new cases of illness over 15 months, not popular, each horizontal line. So that represents your numerator, basically. You don't know how many people are being observed over time. Your numerator could be cases, new cases, that's the arrow down. It could be the number of dead or death. It could be the plus sign. So total person time for denominator is computed by either summing the amount of person time contributed by each person, a small cohort, or by assuming the average size of the population being followed up if it's a large population like a city, a community, a state, a region. Okay? So you assume the size of that population in the middle of the year, you're doing follow-up in person years, you multiply by one person year. So City of Columbia, Missouri, 110,000 people, it's 110,000 person year of observation. And I'm making no mistake in doing that, so large that the binomial approximates the Poisson, remember? Whereas if I have a small number of people, I actually have to count how many weeks of observation they gave to the follow-up and say this person contributed in these 12 months only 5 months, the other one contributed 6 months, the other one. So I sum them up and I end up like 1,000 person month of observation out of 100 people. Okay, that's your person years. Here's another example. Here you have 1, 2, 3, 4, 5, 6 people, A, B, C, D, E, F. So you're 6 people being followed up over time from 0 to 8 months. So it's an 8 month observation period. So now let's count the person year of observation of these people. Okay, the first person, person A, contribute how many months of observation? 1, 2. Okay, we got a problem here. How do I get back to the? It's going too fast. Okay. Sorry, folks. Passei? Não, não é isso não. É esse aqui. Ok. Porque eu acho que ele está com... There's something moving very quickly. So you have 3 months for the first person. C has subject A, followed for 3 months, followed up for 3 months, person B for 8 months, C by 4 months, D by 8 months, E by 6 months, F by 2 months. And here's the total person time, 31 months of observation. And how many cases develop the condition? X is the number of, well, every time a case occurs, I call an X. So person A developed the condition of my interest. Oh, God. That's annoying. I don't know what's going on here, folks. Sorry. Bear with me. So this person here developed at month 3, the other one developed at month 2, about month 2. So you have 2 new cases divided by 31 person years of observation. So your instance rate is 6.45 per 100 person month of observation. That's a rate. That's not a risk. That's your rate. So another example, I have 2,010 men enrolled in a study, followed up over 4 years. Let's count, and the interest here is heart disease. Let's calculate the person time incidence rate, assuming that person diagnosed with disease or lost to follow-up in any year here is going to get half of the years. I'm assuming, because I'm not measuring every week, every month. I'm measuring once a year. So I don't know exactly when they did. Thus contribute half the year to the denominator. So after year 1, I had 2,000 people being followed up plus 100. That's how 2010. I lost 100 at the end of the first year. So next round, by the second year, I'll have only, 2,000 follow up. Out of the 2,099 developed, were lost, and 1 person developed the disease. So now I end up with only about 1,900 people to follow up in the third year. And out of those, I lost 693, and 7 developed the disease. Man, this is going to kill me. Não, estou apertando a setinha, não estou aqui, ó. Vou deixar aqui. Yes, and so on and so forth. So you got the drill here. You got the drift, how this is working, right? So let's calculate. God, cannot go back to forget it. Number of cases diagnosed, trust me, 1, 7, and 8 altogether for each period that I was observing. So it's 16 cases, new cases. The person years, you already know how we calculate, right? 2,000 multiplied with the 2,000 people gave a full year. 100 people gave me half of the year on that first year of observation, and so on and so forth. Start calculating like that. You end up with 6,600 person years of observation. And the incidence rate is going to be then 16 new cases divided by that 6,600 person year. It's going to give you this value, which is 2.42 per 1,000 person years of observation. Okay? See how that works?
Professor, I don't understand this equation. 0.5 plus.
Remember I told you when the person is develop the condition or is lost to follow-up, I give them 0.5 of the year, half of the year. Instead of 1, they're getting half of the year. So, stand. Oh, it worked. So 2,000 people contribute a full year. Nothing happened to them. 100 people, something happened to them. Either they are lost or developed the disease, multiplied by 0.5. They all give only half of the time. So they contribute 50 person years of observation. 100 people contribute only half of their 1 year period of observation. Because I don't know when they develop the disease or when they are lost to follow up. Okay? And so on and so forth. That's what we're doing here. So you end up with this incidence rate. Very different than the risk. The risk will have been 16 divided by how many people I have here? I have to go back. Sorry. My follow-up has 2,300. 2,100 men. So 16 divided by 2,100 men is not the same as 2.42 per 1,000 person years. It's a completely different number. I told you the risk and the rate are different things, unless the numbers are very large. This is getting to large territory. You're going to see the rate and the risk are not too far different, but that they are going to be different, significantly different. It's too small. Okay, let me go back to mode presentation for you all. In contrast, the incidence proportion, oh, I was here. It was 7.6 cases. You see that? During the follow-up period, an average of 1.9 cases per each person 1,000 years. Whereas I found 2.42, 2.5 per 1,000 person years. Okay? If I was using the risk to estimate the incidence rate, I would have made a mistake. Remember the risk and incidence rate? I can use that formula 1 to the minus exponential to the rate multiplied by time. Okay, that can give you an estimation of risk, but it would have been 1.9 per 1,000 person years, when in fact it was 2.42, 2.5 per 1,000 person years. So for a number that are not too large, you're talking about 10,000, 100,000, 200,000 million, they are going to give the same number. But usually when you do a territory that's small numbers, 1,000 people, you better use each individually, risk and incidence rate. Okay? So we already know that. For calculation of disease or injury incidence measured in a large population, I gave you that. You estimate the incidence by dividing the number of new cases A by the person time estimated, which is the size of the population, half of the year. Usually census estimates are done halfway through the year, in June or July, depends on the country. That's your census estimation of the population size. So in large population, cities or counties or region, highly populated, you just use that number as your person years, because you're doing person year and multiply by 1 anyway, right? And you assume that everybody who entered that community and left that community, the number coming in, the number going out are about the same. That's another assumption you make when you do this approximation. Average size of the population multiplied by the length of observation for your total person time of the denominator of incidence rate. You assume that population is large, very large, and you need to confirm that. And second, you assume that the number coming to this population, the number leaving that population is about the same. The number of people leaving, dying, or migrating, number of people migrating in, number of newborn, about the same.
Can you apply this equation to COVID-19 scripts?
Yeah, absolutely. As long as it's large numbers, you're dealing with entire cities. God, I don't know what happened here, but this is just another example of 55 per 50,000 person years incidence rate, which is the same. It's another way to present. You can multiply both sides by 2, the numerator denominator by 2, you end up with 110 cases divided by 100 person years. You like to present your cases for 100,000 person years or for 1 million person years, 10,000 person years, okay? So you just do the arithmetic to get the numbers right. You can also present, as bars like that. So because we talk about incidence rates, there's always a formula for calculating the confidence interval on that incidence rate. If you found the incidence rate to be 2.42 per 100,000, that example I gave you, what's the confidence I have that this is the true number? I can say if I could repeat that experiment and estimate rates like that out of the population over and over, 1,000 times, 100 times, I will obtain this rate X% of the time. And the number will be between that and that. That's your confidence interval, okay? So that is a little bit more complicated formula. I want you to read about it because I can't calculate for you because it's an iterative process in which you have to estimate your Y. Well, Y is your estimation for the N, for the incident cases in the top of the incidence rate formula, okay? So you have to estimate that by using a chi-square distribution for X of 2 degrees of freedom, and then for alpha minus 2, which is 0.025 in each tail of the normalized distribution, or in this case, chi-square distribution, which is Z square, is the same standardized distribution square. Okay, it's a much tighter confidence interval. So, and then you develop the UI and YU sub U, which is the unexposed, exposed, and unexposed. And you calculate the incidence rate using this complex formula here. Most people have tables that can calculate that for them based on the chi-square. I don't want to show it to you here. Say there are 14 events are observed in 200 people studying 1 year. The percent time risk is this much. And then you have 14 events. You know how to calculate the rate. If I applied that formula, I did. I'll give you a formula how to calculate that in Excel at the end of the course. You end up with this confidence interval here. I just wanted to be aware. Softwares give you that. You don't need to do it by hand anymore. Okay? But there's another way, an easier way to calculate. It's an approximation for large numbers. Okay? If the number of events is large, okay, so if your number of events, you're not talking about 2 or 3 cases of cancer out of a million population, but it's still rare, but a very sizable number of cases, 100 cases, 200 cases, 300 cases. So in this situation, or even a little bit smaller, 30, 40 cases, you can calculate using that formula. The upper limit is going to be 1,000 divided by N, then multiply D, quantity D, plus 196 plus square root of D. Okay, and I'm going to show you how to calculate D and N. D is the number of events upon which the rate is based. And N is the denominator of the rate. Okay, manner rate is expressed, could be 1,000, 100, and so on. So the example here is in Clearfield, I think it's Indiana. There were 21 resident deaths due to motor vehicle accidents for a population of 84,497 individuals that year. The crude incidence rate, you know how to calculate. The population estimation is about right. It's a large number, so I can use that as the person year. There's 84,497 person year. Gave rise to 21 new cases of motor vehicle accidents for a crude incidence rate of 24.9 deaths per 100,000. So I'm going to apply the formula now using those numbers. Okay, folks? So here's the square root of 21. So you do the square root of 21, remember, because D is the number of cases, number of new cases. That's your event, your D. Okay, square root of 21. And then you multiply that value, apply 1.96. That's a Z value for standardized normal distribution of any possible measure of the incidence. And then you end up with 21 plus that value, 21 minus that value. That's your confidence interval summation and dilution. You have your estimation of the inverse of 84. Remember, we do in the formula is a 1,000 divided by N. Remember? So you have your total 100,000 divided by 84,000, because my N is not 1,000. My N is 100,000. Remember? I calculate per 100,000. So when you end up doing that, you formulate. You can read it again, you get it. That's an easier way to calculate the confidence interval for incidence rate. Every time you have population which is larger than, let's say, 20, 30,000 people, in number of cases, there are more than 10 cases, 20 cases and above. 30 or more is even better. That everything approximates normalization after 30. If it gets to 100, it's even better. Number of cases. The total population has to be large, has to be over 10,000, 5,000, something like that. So you applied that formula, you got your confidence interval for the incidence rate ratio. Another example, and you can apply the formula again, and you get your confidence interval. I want to take some time to go over distinction between crude and adjusted rates. Okay? Accrued rate is the rate that you calculate. In all these examples, I'll give it to you. There's no adjustment to that rate. There's no need. I didn't talk about the need for adjusting. But let's say I'm calculating the incidence of Clearfield cancer or motor vehicle accident in Clearfield, Indiana, with the motor vehicle accident in the city of Columbia, Missouri. 2 states in the U.S., 2 cities, different cities in the U.S. One has 84,000 people. Mine has 110,000 people. There are 14 cases, right? In this example here, if I'm not mistaken. No. Let's say we do colorectal. Jesus. So it's whatever. 3,205 new cases out of 5 million, the whole state. I'm comparing 2 states. If one state is very young in population, okay, let's say, I think I'm going to get you an example later on 2 countries, but one state is very young, the other one is very old. You intuitively, you don't need to be a genius to think about the mortality rate in those 2 places are going to be different, right? Because the older you are, the closer you are to death, or to sleepy, like Fred is sleeping. But anyhow, so you cannot make fair comparison rates when you're comparing things that need to be compared fairly for a decision in public health. You want to say, is my state worse off than the other state so I can ask more money from the federal government? For instance, your public health official. Or is my hospital rate worse than my competitor in my private sector hospital? Is my mortality rate, in-hospital mortality rate, greater than the other hospital? If the other hospital is attending to another community that has a much older population than my hospital, they cannot be compared directly, those rates. They can only be compared if I adjust the rates for the age of the population, otherwise the comparison would be unfair. The county or the place where the hospital located having an older population, you have a much higher mortality rate. It doesn't mean they're doing worse off. The mortality rate in a hospital have to be larger, but not because they're doing bad work in a hospital compared to the other one that's not having such a high mortality rate. You follow that? So is the age of the population a fact? That's called confounding. You should know that from basic epidemiology. And so you need to adjust for that confounding effect of age. So to compare fairly the rates. Maybe there's some other factors, okay? Maybe one city is a lot of young population who migrated out. So not only they are young, but most of the young men left out the city because the economy was terrible. Like Flint, Missouri, Michigan, a city that for the past 3 years lost about 40% of the male population because the jobs are gone and people were left, and the 30% of women left too, but the ratio of male to women is much higher. So you end up disproportion of the gender. If a disease I'm looking at is affected by gender, like cancers are usually by hormones, I'm going to have a problem making a fair comparison. I need to adjust for the gender and the age group. Okay? So in that situation, you need adjustment of rates. So you can read about crude rates. We were talking about crude territory so far. Crude rates, crude incidence rate, crude mortality rate. Remember, the mortality rate is a form of incidence. You can only die once, right? Unless you're James Bond. So that means every death is a new case of death. The new only one. Is that prevalent death? What do you think? Question for tomorrow. I'll answer that question. Can I call death a prevalence? By definition, epidemiology should be an incidence. I'm going to show some interesting thing tomorrow. So again, you have something else you can look at beside crude rates, is the age-specific rates. By doing that, if age is a confounder, in tables like that, I'm no longer confounding. When I say the rate is 5 per 100,000 among those who are 15 to 24, that's 15 to 24. If age is not confounded, everybody has a more or less the same age group. They're all kind of teenagers and young adult, very young adult. The next group is young adults and mature adults, but not so mature. They're still adolescent in their mind if they're men. They are very old if they're women, and so on and so forth. It goes on. So let's say comparison between upstate New York. This is an example. I'm going to cut to the chase because of our time. I want you to read about it. This should be a review for you. I'm interested in showing you a method of adjusting rates so that comparing rates across groups become reasonably sound. You're going to compare things that should be comparable, apple to apples, not apple to pears. Okay? You're going to compare the things that are supposed to be compared. And there are many methods to adjust rates so they're comparable. One is direct method, the other one is indirect. We also can do adjustment through modeling, putting in a regression and coming out with an estimated rate based on a regression, adjusted for all the factors in the regression that you may want to put your hands on. Okay? Standardization or adjustment is necessary in comparing rates. I already explained why. It's a summary rate compared to population that has been mathematically manipulated to remove the effect of the difference in the composition of the population being compared. So I'm falsely forcing population to be the same distribution of age, the same distribution of sex, the same distribution of education, anything they are interested in. If I'm doing hospital death, in hospital mortality, a very important in America adjustment variable is the sin, or it's an index that indicates how morbid the population on average should be because of that index. So if a population, for instance, my hospital is a academic medical institution. We have 4 hospitals. We are a university school of medicine. I'm a professor, deal with patients all the time. That hospital, by definition, and because of the way it's established organizationally, accept all patients, including patients who are indigent patients. They have no money to pay. And all the Medicaid patients. There's another competitor across town, big hospital, beautiful, does an exceptional job, excellent, high quality, but they do not take very poor patient or indigent patient. Do you think the population come to a hospital will have the same level of morbidity than the other one on average? No, mine is going to be much worse. So my numbers are going to always be worse than them if I don't adjust. You with me? Okay, so this index is an index of cross morbidity and severity or acuity of the condition of the patients coming in. The very poor, anywhere in the world, poverty is a major cause of ill health. So the very poor have much higher severity or acuity of their cases. So their hospitals don't take those very poor. They do easy case compared to ours. So our cases are more likely to die, more likely to complicate. So I adjust my numbers using that index of acuity. When I adjust for that index, it takes care of every difference between them. So that's what we're going to do here. And I almost fell. So why adjust? Example, Sweden and Panama. You have total mortality between Sweden and Panama. You have 73,555 deaths in Sweden and 7,783 in Panama. For total population, this one here is 7 times larger than the other one on the right-hand side of Panama. Okay? But let's see how they look like. The crude mortality rate is nearly 1,000 per 100,000 for Sweden and 724 per 1,000 for 100,000 in Panama. So theoretically, look at crude rates, Panama is doing better than Sweden. There are less people dying in Panama than dying in Sweden. Do you believe in that number? I don't, because I know that the population of Sweden is way older than the population in Panama. Okay, if I adjust for age, this whole thing is going to change. The population in Sweden, I know they die much less often than the Panamanian. If I could look at something called survival rate, which is life expectancy, in Sweden is about 81. In Panama, at that point, when this calculation was made 17 years ago, was about 67. Huge difference, right? So I know Panama is worse off, but it looks better when you look at crude rates. Suppose, same thing with hospitalization, just example. So there's 2 methods. One is direct standardization. The other one is indirect standardization. I want you to look and read about direct standardization, which is this one. We're going to go quickly on that. I want to focus on indirect standardization because it provides 2 measures. It not only adjusts, but gives you a very important measure, which is SMR, standardized mortality ratio, or standardized morbidity ratio, if it's talking about hospitalization or incidence, or if you talk about death, it's mortality ratio. So in this one here, you take the age-specific rates, age groups specific, and available for the study. Okay, that's the situation you have. You cannot do age-specific rates like you did in direct standardization. It's not possible. Or you have a small number of events in the study population, and age-specific rates are not stable. You have age-specific rates, but very stable, like hostile comparisons. So you have those situations. You cannot do a direct standardization. You have to use the indirect standardization. So in that way, you choose a stable population to represent the average mortality or closer to an average mortality or incidence experience compared to the study population. Calculate the proportion of this population in each age-specific groups, and then you end up with the age-specific rates for each age group in reference are applied to the study population weights in each group, and the weight is the proportion of the population that group for the study population. Use the structure for your population of interest as a weight and estimate the expected number of cases that would have occurred had you had the same structure of the standard reference population. So you're basically saying, hey, I cannot do direct standardization, but I do have here a standard population. That's neither Panama, neither Sweden. I combine the two populations, combine their size for each age group, for each specific age group, and the number of cases that occur overall. Okay, or I took a standard population, let's say the US population, something between United States population, and I took their rates, the age-specific incidence rate of the disease or mortality rate, and I multiplied that rate by the size of the population of Panama and Sweden in each age group. When I do that, I'm creating an expectation of how many number of cases I should observe. So I'm basically saying, hey, Panama, if your population between 15 and 24, age between 54, okay? If your population experienced the same force of mortality of the United States in that same age group, that's how many cases of death you should have in this group. That's what you're asking. You multiply the incidence rate calculated from the standard population or the mortality rate in that age group by the total population in the same age group for Panama and by the total population of Sweden, creating an expectation what should have been the total number of cases in that age group. Okay, once you do that, you got your numbers. So you create something called adjusted indirect rate based on multiplying the crude rate that you had originally by the reference standard population standardized mortality ratio. Okay, because once you do this age-specific multiplication, you sum across each age group, you end up with a standardized ratio. Okay, so the AR, the adjusted rate, is the crude rate multiplied by SMR. And what is SMR? It's X divided by mu. Mu is the expectation, is the total sum. Okay, whereas mu is the summation of each age-specific rate by the population size of your study population, summed across all age groups. Example here, okay? You have the standard population United States, you see here, you get the mortality rate, 0.0229 for the group of 0 to 4, 5 to 24 is 0.00062, and so on and so forth. That's your mortality rate for the United States for each of the age groups, okay? You multiply that by the number of people in Zimbabwe on each age group to create an expected number of cases that you should see in that population. Okay? So that's going to give you the expected number of cases because you don't have the number of deaths in Zimbabwe and you cannot calculate an age-specific rate in Zimbabwe. So you end up with something like that. You multiply the US rate by those numbers, population here, in Zimbabwe in the same age group, you end up with a product of these two of US rates by Zimbabwe population, which is R1, R sub I multiplied by N sub I. So this is the expected number of deaths you should have seen it. And then you sum all these deaths, summation of R1, R sub I multiplied N sub I, to obtain 36,390.36 potential expected death. Okay? And then you're going to multiply that number, okay, by the crude rate in the US. the standard population, to obtain an expected, called SMR, standardized mortality ratio, okay, which is the number of deaths that should have occurred if the force of morbidity of death would have been the same between the US and Zimbabwe. And you do the same for Sweden, you end up with two different numbers, and then you can compare these numbers. But also you can multiply that to get your age-adjusted rate, okay? So you multiply 2.72 by that 0.086 value that you found here at the early step, okay? And you end up with your so-called age-adjusted death rate, 20, or cases, 23.35, that's 2,335 per 100,000 deaths. That's your adjusted rate. This is an important number that goes a long way and is very much in practice. I'll give another example. You combine the two populations to create the standard, and then you calculate. Pay attention to that so you can give me, a little bit of your insight, how this affect your view. What was the comparison of the two populations? This is all review for all of you, because in practice, what is going on here? I don't know how that happened, but it did happen. Okay. I can see you. So I gave you that early on, so I'm not going to debate too much about it. So we gave you an indirect method of adjusting rates so people can compare two things are different, supposed to be different. Read the other one, direct standardization. It's much easier to understand. This is a little bit more complicated, but read the steps and see where the numbers are coming from, okay? Why is that important? For what I'm going to try to teach you, it's not too important. That is a review of basic epidemiology, and you should learn that, should have learned that early on. So that's another point for you. This stuff that I'm going to show you now, the relationship between incidence and how much is my time now, Fred? 15 minutes left? Okay. So I already gave you a little bit of that. Let's go back again. It's a little more cleaner. I showed you that too quickly when I was doing the so-called rates and where they're coming from. I don't know how this happened, but it's all messing up. So this is a way to estimate the incidence for rate from the cumulative incidence of risk, or vice versa. You calculate risk based on the incidence rate, okay? You know how algebraically to move this 1 minus exponential of minus IR multiplied by D. You know how to turn that into the inverse. You solve for IR to get the risk. You can do either way, okay? I'm going this way because it's not moving in the right direction here. We gave you that already. These are more examples. I just want to make sure I have good material for you to review it. This is much clearer than the slide before on how the incidence density or incidence rate can be used to estimate the cumulative incidence of the risk. This is all review of your prior epi stuff. Yeah. Period. Prevalence. Okay, we're supposed to cover prevalence now, but we did early on, just to simplify the difference between prevalence and incidence, you already know, and how they relate. The average duration of disease and the incidence rate are related. And I don't think I have anything else. I wanted to finish 10 minutes early. We finished 15 minutes early. Okay, so there's more questions here? No. Yeah. So read the material, send emails to me this afternoon. I'll answer all of you. This is a review of basic app. You should have it because give you the foundation of the three measures: incidence rate, cumulative incidence, which is risk, and prevalence, and where they're coming from, the statistical distribution. Because later on, when you go to do evaluation of intervention, you're going to see statistical testing and regression. And why are we doing that? Well, you need to learn where those distributions are coming from. That's why you end up covering a lot of stuff in one short period of time. Okay, folks? So I'll be seeing you tomorrow, but the fun is really going to start halfway from tomorrow lecture all the way to the end. That's when we really look into different methods, how to design study to evaluate intervention. What we're doing today and a little bit of tomorrow, just a review of the basic stuff so you don't get lost when you talk about risk ratio or relative risk later on. Okay? Thank you all for being wonderful audience. Didn't ask me any questions. I don't see you. Best. Bye. We can close it. Have a good day, folks.
Thank you.